This very short podcast will talk about the impact of intermolecular forces on the behavior of liquids. But this slide gives you a quick rerun of what I hope you already know. The three common forms of matter, gas, liquid, and solid, differ from each other in their degree of disorder. So gases have total disorder, lots of empty space, particles bebopping around inside the container, and the particles are free from each other, relatively speaking, in terms of intermolecular forces of attraction. They don't attract or repel. Liquids have more disorder than a solid, less disorder than a gas, and the particles, though, are much closer to each other. They still can flow just like a gas can, but have much stronger intermolecular forces of attraction. And of course, solids are the most ordered form of matter, showing an orderly arrangement. The particles are in basically fixed positions that are close to each other. And to change from one form to the other will involve either adding or removing heat, and or in the case of gases, changing the pressure. So let's take a look at some properties of liquids. Liquids are denser than a gas. They're basically not compressible. You can compress them somewhat, and I believe this is the basis of hydraulic systems that are in things like tractors and planes. Liquids do have fluidity, the ability to flow, and they're more fluid than a solid and much less fluid than a gas. Now there's a term about liquids that you need to know the official definition of, but then let's look at it in a practical context. Viscosity is resistance of a liquid to flow. The stronger the intermolecular forces are that hold that liquid together, the higher the viscosity. Let's take a delicious example. Maple syrup on your pancakes or French toast. When you get it out of the refrigerator, you pour it, it just kind of oozes out. But if you warm it up and break some of those intermolecular forces that are causing it to be resistant to flowing, then you get more runny type of maple syrup. So a liquid flows by sliding molecules one over the other. When temperatures change then, what would happen to the viscosity of the oil inside your car? Well, we put oil in cars to lubricate the moving parts. Viscosity will decrease. That means its resistance to flow gets less, or in plain English, it gets runnier when you warm it up. So if you've ever put oil in a pan and heated it, you can see that it can go from being kind of thickish to more less viscous and more runny. And the added energy makes it easier for the molecules to overcome the intermolecular forces that are preventing the molecules from flowing. So that's what viscosity is. And oils are created in the manufacturing plant with specific viscosities depending upon what is the purpose of that oil, what kind of engine is it in, and what kind of environment is that engine expected to operate in. So viscosity decreases with increasing temperature. Now there are different blends of this motor oil. So because there are different temperatures in the summer and the winter, you have to have oils that can flow even when it's colder temperatures, and yet oils that don't get so runny that they don't have any lubricating effect in the heat of the summer. So when you look at an oil can, for those of you intrepid enough to change the oil on your own car, what you're trying to do is make sure that you have the right oil for all temperature conditions. If it's cold in the winter, it's still got to be able to flow, and if it's too hot in the summertime, it still has to be viscous or thick enough to get between the moving parts and do its lubricating function. So that's why there are blends of motor oil, because of different temperatures versus summer and winter. Now, another factor that influences the viscosity is the length of the chain. A lot of viscous substances are long hydrocarbon chains, and it's kind of a common sense thing before we get into chemistry gobbledygook. See how long the decane chain is? Relatively short hexane chain. It's like having long hair. The long hair has the ability to become more tangled, and the same with the chains of these organic molecules. So there's an actual measurement to viscosity, this unit little c big P. You don't need to know it. Notice that as you get longer and longer chains, the viscosity is increasing. How do you translate that? It becomes more resistant to flow because the intermolecular forces between the longer chains make them stick to each other more, and so they get more gooey as you pour them out of the bottle. So viscosity can be influenced, as long as they're all at the same temperature, by the bigger the molecule, the more viscous or resistant to flow it is. There's another very important property of liquids, and especially for water, that's called surface tension. And essentially, I'm going to use a diagram to try to explain it. When you could see with superhuman vision from the side view, say, a container of water, you would see that molecules down below the surface have pretty even intermolecular forces of attraction between it and all the molecules around the center atom or molecule. That's why those 4 green arrows are the same length. But if you are a molecule on the surface, there's an uneven distribution of forces between you and surrounding molecules, and the other problem is there are no molecules above you on the surface. So what happens is the surface molecules are only attracted kind of inward towards the molecules that are below them or around them. And essentially you get something that looks like this picture here in the bottom right. It makes the liquid behave as if it had kind of a skin, because you can see just by looking at it, see the space between these molecules up at the top? They're looking like they're atoms, so we're going to pretend that they're molecules. Down here, the spaces between the molecules are much wider. So the uneven distribution of forces between the surface molecules and the bulk of the molecules below them creates something called surface tension. Now, we often think of surface tension as a thing, this thin skin on the surface of liquid water, for example. But really what it is it's an amount of energy you would have to apply to break those intermolecular forces of attraction and kind of spread those molecules at the top out again to increase their surface area by a specific amount. It doesn't really matter how you remember it, but what you can remember are some very vivid examples of how surface tension works. The strong intermolecular forces cause a high surface tension in water, but you can have an even higher surface tension in liquid mercury, which of course we put in mercury thermometers. And that's because liquid mercury, even though it's a liquid, still has metallic bonds which are much stronger, those are true bonds, than the intermolecular forces like a hydrogen bond in water. So here's a lovely nature example of something you might have seen here up on Mount Tamalpais. In the quiet pools of streams, water has a very high surface tension, and when the water is not flowing very strongly, you can see these little water striders appearing to walk on water. And everywhere where you can see his little feet touching the surface of the water, you kind of get a feeling for, hey, that's that surface tension at work. Remember, it's not a thing. It's an energy required to break down that thing, but it kind of feels like there's a little film on the surface of the water. In very extreme cases, you can get this cute guy. This is a basilisk lizard, also commonly known as the Jesus Christ lizard, performing the miracle of walking on water. And one of the coolest things I ever saw when I got to go to Costa Rica 2 years ago was out of the corner of my eye, I saw something run by, and it was this little lizard doing exactly what this guy is here, just running on the top of the water. It was pretty trippy. It was after a butterfly. And as long as he keeps moving, doesn't stop, he's also got that long tail that he can use for both balance and possibly also to get more surface tension. He can run across the surface of the water to escape predators or to catch prey. Surface tension can be seen when you use a soap or a detergent to wash dirt off of clothing or off of dirty dishes. Soaps and detergents decrease surface tension, and the way they work is they disrupt the hydrogen bonds that are between water molecules. Now, they're called a surfactant because they act on the surface. That's where the name comes from. But the way they work is they'll allow the water molecules to get farther away from each other by breaking down the attraction between the two water molecules, the hydrogen bonds. So you can't just rinse off greasy dirt by putting it under cold water. We learned that like dissolves like. So polar substances like water cannot dissolve nonpolar substances like greasy dirt. So if we can use a soap or a detergent to act as kind of an intermediate between the polar water and the non-polar oily dirt, then you can actually get things clean. So surface tension is disrupted in water by the addition of a soap. And we will do a very fun lab where you get to see the impact of soap on the ability to create large bubbles of soapy water. The bigger the bubble, the better the job the detergent had as a surfactant in breaking the intermolecular forces of hydrogen bonds between the water molecules. Another important factor in nature is the use of capillary action in plants. Now, you might not have thought about it too much, but those redwood trees that we have here in California that could be like 300 feet high are having to fight the force of gravity to get liquid water up to the growing tip of a plant. And they do that through a process called capillary action. Capillary action can be broken down into two types of forces. Cohesive forces are intermolecular forces that bind molecules to each other. So if you think of co meaning with, like we cooperate or we co-author, we work together with someone. Cohesive means that the molecules or particles bind to each other. Adhesive forces are thinking about things like glue that stick to some things to other things. Adhesive means that there are forces between a molecule and the surface of the container that it's in. So let's take a look at a picture just explaining that. When you look at liquid water in a narrow tube, like a graduated cylinder, you can see that curved meniscus up at the top. This is kind of an exaggeration. And the reason is that the molecules that are closest to the glass have adhesive forces of attraction to the glass itself. And if the adhesive forces of the water to the glass are stronger than the cohesive forces of water molecules to each other, then the molecules kind of ooch their way up the side of the glass. And that's why you get this U-shaped meniscus for something like liquid water. In that picture, the adhesive forces must be stronger than the cohesive. Adhesive, the ability of the molecules to be stuck to or attracted to the surface of the container that they're in. Cohesive is the attraction of water molecules to each other. But in this example, if you look on the right and the box on the bottom, when we look very closely at a mercury thermometer, now we have this meniscus that's curved sort of downwards. And when we read the temperature on a mercury thermometer, you read it from the top of the meniscus. When you read the volume of water in a graduated cylinder, you read from the bottom. If in water the adhesive forces are stronger than the cohesive, then it should be clear that in mercury, the cohesive forces are stronger than the adhesive. They stick to each other more, than they do to the sides of the glass that they're in. So that's sort of a cool, interesting thing, and one of the reasons why we do use mercury as a liquid inside of thermometers. Finally, to get back to how do plants get liquid water up to the top of quite large plants, like trees, is they use capillary action. That gets better and better the narrower and narrower that you make the tube, which is why the phloem and the xylem in plants, the circulation system, kind of like we have arteries and veins, plants have phloem and xylem, tubes that allow the passage of water and nutrients up and down. Well, when you make the tube really narrow, what will happen is that the liquid water, which is usually the solvent, grabs to the side of the xylem, I believe, and it ooches its way up. It pulls up the other liquid with it by the forces of adhesion. So they're able to beat gravity by using adhesion to stick to the inside of their blood vessels and cohesion stick to each other to be able to get water and nutrients up to the growing tip of a plant. So that's called capillary action. We'll stop there and talk about the not so scintillating concepts of solids in the next podcast. Until then.